Okay. Good noon, everyone. So welcome to lecture number 39. Yeah, so I just removed the announcement slide thinking that there is no announcement to make, but there are a couple of things to announce. Yeah, so this is regarding question number 3 for quiz 1. Okay, so there are lots of issues about people have raised regarding the evaluation of induced path as well as cycles. Okay, so yeah, so what I have decided is I just gone through the queries yesterday. So, but I have decided that I will go through all answers, everyone's answers. So the thing is, so one at least unfairness issue is, so because of the question, nobody should get punished. Okay, so in the sense that for the same question, the marking scheme should be similar to for all attempts. So one thing is for cycles, if you do greedy algorithm, you may not get a cycle. You will have to do a backtracking. Okay, so we have given marks on full marks to those who have constructed a cycle, at least if the graph has a cycle. But the point is greedy may not work. Okay, so greedy will not give you a cycle because you will have to do either a DFS or BFS to get a cycle. Okay, so which is basically a backtracking algorithm, not a greedy algorithm. So I'm going to reevaluate it. Okay, so the current marks will not be reduced for anyone, but for the variance, induced path as well as cycles, there might be an upward revision of marks, provided if you have written a greedy algorithm, you're going to give full marks. Okay, so I'm going through all that, but I'll also go through everyone's sheets so that I'll get to see. So similar types of answers, I mean, in the sense that attempts, efforts, similar efforts will get similar marks. That's what I'm going to ensure. Okay, because the questions were different. I mean, ensuring such uniformity is a bit difficult, but yeah, we have no choice. And second thing, so again, a reminder about this 72 hours limit. Okay, so please don't forget. So those who have opened the questions yesterday for quiz 2, please remember that you have to submit within 72 hours after opening. Okay, don't miss that, because otherwise it will mess up. Okay, so it will be difficult. The system will not allow, and allowing email submissions and all going to be painful. So please remember that. So please also remind your friends. I mean, if there is someone who is absent-minded and will forget and so on. Okay, so that is the second thing. And for quiz 2, so I think there was one graph. So if there is any unweighted edge, I mean, that could be because I was drawing graphs in haste or whatever. So please assume the weight as 0. Okay, that is one uniform. You can just say that, okay, unweighted edges we are assuming as weight 0. Just write it and then run the algorithms. What's all. Okay, so these are the two things. Is there anything else I wanted to mention? Yeah, so this quiz 1 revaluation, I will try to finish it over the weekend. Okay, so I'll have to go through all PDFs of all answers. So yeah, so please be patient with it. And
Hello, sir.
yeah.
Sir,
So will it be
quiz
done?
1 question 4 is the answer. It is there in the Google Drive.
Which one?
Question 4. I guess you did up to question 1,
No,
2, 3.
question 4 that I didn't write the answer, so I thought I will discuss it.
Okay.
So I'll put it. So what I'm planning to do is for assignment 2 as well as question 4 of quiz 2, I'll create a video and upload it. Okay, so for discussion, I don't think it is feasible anymore. Will not have enough time, so I'll just upload videos. Okay, so that
Okay.
see, I will try to avoid writing answers. Okay, I hope you understand it. I mean, I'm
Yeah, sir. You
formally
can
writing the answer, because see, the problem here, I mean, the whole process, right? I mean, the problem here is like it's sad aspect. Okay, it's a sad aspect of Indian academia. So people don't understand. People are not taught what is copying and what is not copying. Okay. And there is nothing, I mean, I don't know whom to blame. I mean, because I have seen even in school, even in my school, assignment was just to copy something from the textbook. Okay, so it's only later I have realized that it's not right. So writing something without really attributing to it is not right. So this is the whole problem. It's the whole reason why the question papers have to be designed this way and so on. All these mess ups happen. Another thing that I want to mention, I mean, if there is some tendency of doing it, is in a relative grading system. Okay, so particularly those who are giving their answers, helping others. Okay, so you are only destroying yourselves because it's a relative grading system. Okay, if someone else gains out of you, you are going to lose. Okay, it's not an absolute system. Okay, so that way it's not really in effect helps, but it's a human tendency. Okay, so discussing or whatever, sharing things and so on. So that is what makes everybody's life difficult. So that is something, so please keep that in mind. Okay, so it's not, you're not helping the other person, you're actually destroying yourself as well as you're destroying the other person. At least one piece of advice is, even if you do incorrect answer, write that, get whatever. See, there will be some partial grade, right? You'll not be given 0. Okay, some non-trivial attempt we are going to give some marks. It's not like we'll give 0. Okay, it's not like, okay, 0 1, except true false thing, that we cannot help. But other things, it will never be like 0. Some attempts will bring in. Okay, so whatever you have understood, apply that and write. That is the best way. So that makes a system much easier, much smoother for everyone. Okay, otherwise we'll be spending a lot of effort seeing plagiarism and so on. It's not a healthy system. This is not just for this course, I mean, it is for future, wherever you are. Okay, that is something that is practice has to come. I don't know whom to blame, because I have seen, I mean, I have experienced it myself. I have also seen school children and so on. They'll be asked to just copy from the internet and present something. Okay, so that's not how it should be done. So I mean, it could be pressure of the volume or whatever. I mean, there could be reasons why society is behaving like that, but that is something. But in the meanwhile, I have also seen answer scripts who were pretty independent. Okay, I really appreciate that. That is how it should be. Even if you are incorrect, write whatever you have. Okay, so in fact, you might have seen some of the answer sheets I have just written. So it's a good attempt, though answer is incorrect. The attempt has to be appreciated. Okay, so that is the main thing. I mean, so whenever, even if you are making an incorrect attempt, right, even if you are not capable of solving, I mean, you know that, okay, you may not be able to solve it, but the thought process, that the failed thought process, right, that is also important. That is what makes you learn. Okay, so yeah, so with this, yeah, I think I had something more to mention. I don't recollect now. Okay, so I'll share it later. Okay, so yeah, somebody
Hello,
wanted
sir.
to say something? Yeah.
So will question 3 evaluated for all?
I won't reevaluate for all. Say first 3, I think it is fairly clear. Okay, so because greedy algorithm can output a maximum feasible object, but whereas for induced path and a cycle induced path, I think it can still output, but whereas cycle you cannot. Okay, so you cannot ensure that greedy will, there has to be a backtracking. So that is something that we are going to focus. Okay, somebody wrote greedy algorithm, we are going to give full mark if it is greedy. That's it. Okay,
For those who had the question of induced path and forming a cycle, for those
cycle, yeah, others only as per whoever raised the issue will be resolving it. I think TS said they have already resolved many of them. Okay, so the others which they left to me, I will be going through them. Like I said, I'm not going to reduce marks. So see, there were also situations, I think some places for induced, I mean, sorry, for the cycle problem, right? So we had given full marks for those who generate a cycle, but then the algorithm will not be greedy. So we have given full marks, we'll just leave it at it. Okay, we are not going to reduce the marks there. Though, okay, what we had asked for was greedy. Okay, so you have given a feasible cycle, it's fine. I mean, a cycle, it's fine. But those who have just wrote greedy but didn't get a cycle, we'll also give marks for that. Okay, so induced path, I'll go through the solutions. Okay, see what are the solutions and so on. So induced path, at least greedy can give induced path always, but I feel people haven't understood what is induced path. Okay, so that's why I'm going to be lenient there. Okay, so see the remaining 3 questions, right? It was easy to understand what was it. So induced path, it may not be that easy to understand what it is. Okay, so we'll be a bit lenient there. Okay.
Excuse me, sir.
Yeah.
Sir, I have a problem regarding grading of question 4. I have also mailed you. So please.
Yeah, that those things I will see. Yes, all mails are there in me. I mean with me, so I'm going to look into it. Okay, so don't worry.
Okay, thank you, sir.
Yeah.
Induced path questions.
Yeah.
So the algorithm which I wrote is just giving a path. It's not giving an induced path, a realized later.
No,
So
we'll see. Okay, so that those things I'm going to go through it. So if you have any issue that you want me to keep in mind, just drop me an email. Okay. Yeah. So I have just marked all the emails and I'm going through. I mean, when I open up this question paper answers and so on, I'll just see email. Is there any issue being raised about this and so on?
okay.
Go through it. Okay. So you see, my purpose is to ensure fairness. Okay. So this. See, you should also understand that it's very hard to generate equivalent questions. Okay, so that is why we end up changing these parameters and so on. But there should be some interesting question too, right? So that's exactly the reason why this greedy algorithm thing was given. But it's difficult to get too many such questions. Okay, so that is why this cycle thing, later on I regretted. I mean, I cannot do anything about it. Okay, so but I wanted objects that is easy to understand. Okay, so there are other objects could have easily given, but it's very difficult for one to comprehend it. I mean, unless you have seen it before. Okay, so that is why path, cycle, or even induced path, it's only the term that is painful there. Otherwise, it's not difficult to understand. Whereas if I want to give you dominating set or other objects, right, other than click independent set, it's very difficult to comprehend. Okay, so that's what I wanted to avoid, because those things I can easily give you questions for greedy algorithms, but then definition is complicated. But the cycle thing, what I missed was like a greedy algorithm cannot build a feasible cycle. That was something an oversight from my side. Okay, so yeah. So again, if you have any issues, please shoot me an email by today itself. I mean, I'll just be sitting on it over the weekend so that I can do it in one shot. Okay, so I don't want to do it. Okay, as and when email comes, process it. That's a very inefficient way of doing it. So I'll get into the context and do everything together. So then it's easier for me also. Okay. Okay, good. So let's get on with the lecture stuff. Yeah, so again, the plan is, so next week, 4 lectures we will have. Okay, so today I'm kind of winding up flows. There will be a small portion left over. I'm thinking of making a video for it. Okay, so particularly algorithms for computing max flow. And next week, 3 lectures I plan to spend on complexity theory. I mean, in the sense that the limitations of algorithms, formalizing it and proving NP completeness or NP hardness. And the last lecture I plan to summarize, okay, summarize and maybe give advices regarding exams and so on, okay, I mean the end sem exam and so on. Okay, so just to recollect, in the last lecture we defined flows. So here we have a directed graph where edges come with capacities, okay, so we'll assume that these are non-negative numbers. Maybe, I mean, we can also assume them to be integers, non-negative integers, but in general these are real numbers, okay. And we'll be given 2 vertices, S and T, distinct vertices. So we call S as source and T as a destination or terminal. Okay, T for terminal. So yeah, one more thing is, so directed graphs with the capacities, people also call them as flow networks. So I might be using the term flow network. That basically means a directed graph. Okay. So a flow is basically an assignment of values to the edges. Okay, subject to the conservation property. So all vertex except the start and the terminal or source and destination should conserve the flow. So whatever is coming in should be going out. It should not be staying. Okay. So that's usual with the transportation networks, a pipeline or a network, right? So whatever, so the intermediary nodes, right? They will always be conserved. I mean, in the sense that they will not, there should not be a leakage there. Okay. So for example, if you think of water pipeline or a gas pipeline and so on, except the source and destination, only thing is there could be multiple sources and destinations in such networks. So for simplifying, so we just take single source and single destination. Like I had mentioned to one of the, as an answer to one of the questions yesterday, if there are multiple sources and multiple destinations, you can modify the network so that you have a single source and single destination. Okay. Yeah, so this was the example that we had discussed yesterday. I'll move on. Okay. So a feasible flow is something which satisfies the feasibility condition, that is capacity constraints are met. So flow assigned to every edge is within the capacity. Okay. So one thing is, in a flow network, we don't really insist on the graph being acyclic and so on. There could have been a backward edge this way. Okay. Such edges are allowed in a flow network. Okay. So that it's not so disallowed or whatever. So only condition that we want, so it could also be that the capacities for two directions are different. Okay, unless you have a network which is like bidirectional network, say maybe a water pipeline, where the capacities could be the same for each direction. Okay, but in a water pipeline, both direction simultaneously water cannot flow in both directions. So you might as well assume it as a directed network. Okay. So we gave definition for value of a feasible flow. Okay, so if F is a feasible flow, feasible ST flow. Okay, so now onwards I will not really speak about S and T. It's understood that whenever I talk about a flow, there is a source and a terminal. Okay, so the flow will always be termed as ST flow. Okay, so the value of the flow is the effective flow out of S. Okay, so that is, you look at all outward edges, look at the flow that goes out. Okay, but there could also be incoming edges, so you look at all incoming flows, you subtract from the outgoing flow. So this is the effective or net outflow. Okay, so one thing that we can easily argue is, so by the conservation property, for any other intermediary vertex, the flow has to be 0. So hence, the effective outflow at S will be equal to the effective inflow at T. That is all sum of incoming flows minus outgoing flows. Okay. So this is one interesting property. So I could have defined value of flow as this. It's the same quantity as the effective inflow at T. Okay. So only difference here is I'm looking at the incoming edges to T here and then outgoing edges. So here looking at outgoing edges first and then subtracting the value, sum of values or flows for the outgoing edges. Incoming edges. So it's outgoing first. Okay. So this is an example again. So value of this flow happens to be 10. Okay. Yeah. So the rest of the lecture we are going to look at structure of flows. Particularly, we will be interested in maximum flows. That is, flows which optimize the value, that is, which maximize the value of the flow. Okay. For that, so we need certain notations as well. We also need the notion of cuts. That's what we are going to introduce now. Okay. So first, I'll introduce one notation. This is following Jeff Erickson's book. So there are also other books which follow slightly different notations. Okay. So for any vertex V, so we define the net outflow of V. Okay, so defined by partial of Fv, okay, or dou of Fv. Okay, this basically talks about the boundary or whatever. Okay, so let's not worry about the terminology. It's basically a differential, but let's not worry about why the notation is used. But the notation basically says what is the net outflow out of this vertex. So it's basically, you look at all outward edges and sum their flows, and then deduct from it, look at all inward edges and deduct the sum of the flows at all inward edges. Okay. So for example, let's look at this example. So for this vertex, so del Fs is, so there is no incoming edge in this graph. Okay. So then it's 10, 0. Okay. So del of Fs is 10. Whereas here, so there is one incoming flow, value 10, outgoing flow 10, 0, 0. So this, for this, del F is incoming is 10. So 10, outgoing is 10 plus 0 minus 10, which is 0. Okay. So similarly for others, you can compute that these are all having value as 0, or the del value as 0, okay, or do. I don't know what is this, how it is pronounced. Okay, and here it is net incoming. So del ft will be what? So outgoing is 0, 0 minus 5 plus 5. So it is minus 10. Okay. It has net incoming flow. Okay, so if the del value is negative, that means it's a net incoming vertex, okay, or inflow vertex. Okay, so some observations. Okay, so by the conservation property, if you sum the net outflow or DAO values for each vertex, okay, so remember that the values are non-zero only at S and T. It could be that it's 0 there too, okay, but it's non-zero only at those two vertices. No other vertex will have del value non-zero because of the conservation property. So this happens to be, the summation is equal to dou f plus dou t. Okay. Now again, if you apply conservation, so whatever is leaving at S, it has to enter somewhere, but any intermediary vertex, it's not consuming anything. So everything will have to be consumed by T. So in other words, the conservation property also kind of implies that this is going to be 0. Okay, so hence dou fs is minus of dou ft. Okay, yeah. So this is just an observation. I will not write it there. It's not necessary. Okay. Okay. So this is our fundamental question, our fundamental algorithmic question. Okay. So given a flow network with a given capacity, obtain a feasible flow such that the value of the flow is the maximum. Okay. So we want to maximize the net outflow at S or net inflow at T. Okay. So that is the algorithmic question here. Okay. So how do we compute such a thing? So here is an example. So from the previous example, so the first feasible flow that was here, okay, so value of that flow was 10, right? So I marked in red a renewed or a new flow assignment, okay. So where this edge has got a flow of 5, this edge has got a flow of 10, okay, this edge has got a flow of 10, and this edge has got a flow of 10, okay. This edge has got a flow of 5, this edge got a flow of 5. All other edges will have 0 flow. Okay, so flow will be 0 for all other vertices. This is 0. Okay. So now it turns out that this is the maximum value of any S2T flow in this network. Okay. How? I'll tell you very soon. Okay, so we'll know how to reason that this is the maximum. Okay, that is an, see, otherwise there is no easy way to judge, right? I mean, there could be some other assignment. How do you know that this is the maximum? So, modulo that, modulo seeing how it is. So I'm just telling you that this is the maximum. Okay, so this is better than the previous flow, which was, whose value was 10. Okay, so now our objective is to obtain such a flow. So given a network, a flow with value 15 should be given. I mean, given this network, the flow value or the value of the flow output by the algorithm should be 15. Okay, so basically it should be maximum. But the questions that arise is, so how do you know flow is maximum? Well, one thing should be, if every edge meets its capacity, right, then it should be maximum. Then obviously it is going to be maximum, right? If every edge meets its capacity. But then it is not even necessary that all edges meet their capacities. So for example, in this, so this edge is far from its capacity, right? So it has an assignment of 5, but its capacity is 20. So there is still a slack of 15. So here this is full up to capacity, and here this is 0 capacity, and this is 0 capacity. I mean, it meets nothing of the capacity. So flow value is 0. Here it is full up to the capacity, but here it is far, here it is far. So this capacity, so the naive imagination that a flow where all capacities are tight, in the sense that flow assignment is equal to the capacity, that does not hold ground. Here we have an example of a max flow where the capacity is not met. It's so what I mean is the flow assignment is well below the capacity for certain edges. Okay. So this already says that this task of even given a flow, seeing if it is a max flow, so let alone computing the max flow, seeing if it is or deciding if it is a max flow or not, that's already non-trivial, right? Unlike the shortest path problem. See, for the shortest path problem, it's kind of, it's not easy, but you can verify. So given a path, whether it is shortest or not, you enumerate all possible paths and then see, right? So similarly here, a similar way is to enumerate all assignments. That seems to be a much more complicated task, right? So enumerating all possible flow assignments which are feasible. Okay, unlike even shortest path or even minimum spanning tree. Minimum spanning tree, it's kind of easy if you know certain facts. Okay, so so what you do is you just look at edges which are not in the MST and add it. So if there is any one cycle where this added edge is of not maximum weight, then you know that it's not an MST. So there is an easy test. Okay. So shortest path, it's slightly non-trivial, but still there is an easy test. Whereas for flows, there's no easy test but to assign all possible flows, okay, or enumerate all possible flows, which is a non-trivial task. Okay. So that way, max flow problem was kind of challenging task for quite a while until the 1950s. Okay, so in the 1930s or 40s, I mean, even much before, people had kind of studied them implicitly, but not in an explicit sense. So the explicit application was like the one that I had mentioned, the first documented application, that is the military application. So yeah, so that is going to be our main task here.
Hello?
Now. Yeah.
Sir, like I heard this, but I don't know whether I'm sure or not. So you said if each edge achieves its maximum capacity, then then it's the maximum flow. Is it? Did you make that statement? Something like that?
Yeah, that is one possibility, right? So how do
But-
you check? So if everybody reaches their capacity, then it's likely to be the maximum flow, right?
But conservation should also be there, right?
Yeah, conservation will be. That's exactly why. So that condition is not being met. So because of the conservation property, each edge getting to its maximum capacity will not give you the required max flow.
Like may not. I'm not sure, but it may not.
No, in some networks it might, but that's not always the case.
Okay.
Yeah. And the conservation property is what kills everything. Otherwise, you can just assign maximum, right?
Yes, sir.
Yeah. So the remainder of this lecture and possibly part of next lecture, we are going to see a nice insight into this. Okay, so through a dual object called cut. Okay, so we'll see that weight of a cut with respect to this capacity, you're treating this as a weight of edges. So a minimum weight of a cut that separates S from T, that is, it kills all S to T paths, basically is equal to the maximum flow value. Okay, so I'll just demonstrate here itself, and before introducing the formal terminology. Okay, so a cut is nothing but a partition of the vertices. Okay, so an ST cut is a partition such that S and T are in two different paths. So this is S, this is T. Okay, so this is an example ST cut. Now the weight of the cut is nothing but the edges across. So since we are interested in flow from S to T, so we will be looking at S to T cuts. Okay, so we are only looking at cuts that. Okay, there is some noise. Is there any problem from my mic? I think some of you have turned off on mic. Can you turn off if you are not speaking? Thank you. Yeah, so we are interested in only edges that go from S to T. Okay, so that's this edge as well as this edge. This edge we are not interested, it's coming from T to S. Okay, now if you look at the value of these edges, 5, I mean capacity, 5 plus 10, okay, 15. So this matches with the value of the flow. So I can also look into other cuts. So another cut is this. This is also an S to T cut. But the value of this cut is 20 plus 10, 30. So it's far bigger than this value. Another is, this is an ST cut, okay? That is this vertex in one portion and this vertex in other. So in this case, value of the cut will be what? 10 plus 10 plus 15, that is 35 plus 15, 50, okay? So yeah, so values of cuts are 30, 50 and 15, and you can also take this as a cut, that will be 35. This probably is another cut, that's whose value is 25 and so on, okay? So what we are going to show is the minimum value of an S2T cut will be equal to the maximum value of an S2T flow. Okay, so in this case, the minimum value happens to be 15, and hence it will be the value of the maximum flow.
Hello,
So, yeah.
sir. How are you defining the minimum value of a cut? Are you deciding the minimum weight of the cut set, or?
Yeah, that's what I said, right? You take sum of all weights of edges from S to T.
Okay. Okay.
Yeah. So I'll define it formally. Okay. So that is kind of, I would say, a breakthrough in network flows, but it's not just network flows. Okay. So this viewpoint actually has impacted immensely many algorithmic questions, particularly those of matchings and so on. Okay. So the proof of this statement, in fact, gives us an algorithm, though it's not an efficient algorithm, but that basically gives a framework for all such algorithms. So in fact, efficient algorithms for network flows and hence also matching, they all basically have roots in that meta algorithm. This will be like Ford's meta algorithm or a generic algorithm. Okay, so that is what we are going to see next. So what I plan to do is I'll look at this structure. I mean, we'll define max cut, min cut first, and then we'll relate min cuts to max flows, and we'll see a proof of the statement, and then we'll see that this already gives us an algorithm. Okay, so that's what we are going to do. Okay, so I really like to use the term dual. Okay, so this min cuts basically are dual objects to flows or paths as well. Okay, so GB flow network or a directed graph with SNT given. Okay, an S2T cut is a partition of the vertex set, say S union T. When I say partition, they should be disjoint, that is S intersection T should be empty set, but their union should be the whole vertex set, such that S is in S and T is in T. Okay. Now, if G has, say, edge capacity C, then the capacity of the cut ST, this should be capital, okay, this is defined as, you look at all edges that go from S to T, capital S to capital T. Okay, so I'll just draw it pictorially here. This is how a cut will look like. S sits here, T sits here. This is S, this is T. This should be a partition. So there would be edges in either direction. Okay, this way and this way. Okay. Now what you do is you look at all edges in the direction of capital S to capital T. So that is, the starting point should be in capital S, ending point should be in the capital T. Okay, so you take sum of all those weights. So you look at, I mean, by weight I mean capacity. Okay, so run through all pairs U V such that U is in S and V is in T. You take sum. Okay, so one thing, so I've just written it this way, then it might be a bit confusing. So why should it be that every pair U in S and V in T should be an edge, right? Okay, so what we usually do is for a non-edge, if for a pair, let's say UV, if there is no edge, okay, I'll take the capacity as 0. Okay, so if UV is not an edge, then capacity of UV is 0. Okay. So with that, this is the definition. Otherwise, I would have just written UV is an edge, U in S. So equivalently, I can write it this way: summation UV in E, U in S, V in T, C. Okay. This is equivalent. But for this, I need that capacities for non-edges is 0. Okay. So edges with 0 capacity are non-edges. Yeah. So I'll use the previous example to demonstrate. Okay. So the previous example, again, the whole example thing is from Jeff Erickson's book. Okay. So if I take this as S, see, any subset that contains S and any subset that contains T, such that their union is the whole vertex set. Okay. So these three sets as S and these three sets as T. Then the value of the cut, you look at all edges that go from S to T. So this is S, this is T. So you look at all edges that go from S to T. There are only two such edges. Okay. You look at their capacities, take their sum. So the capacity of this S to T cut is 15. So this is not the only cut. There are also other cuts. Okay. So other cut, I'll just draw it here, but I'll delete it after the lecture. Yes, sorry. Oops. Bad. If I take this as S and this as T. Okay. So can somebody tell me what is the capacity, what is the weight of the cut? What are the edges that are relevant?
35.
Yeah, is it 35?
It's 50, I think.
It is 50, right? See, these four edges. So this edge, this edge, this edge, and this edge. Okay. So capacity will, the weight of the cut will be 50. Okay. Yeah. So I'll be deleting this so that, I mean, it looks neat when you look at the slides. Okay. Yeah. So is the definition of S to T cut clear to everyone?
Sir,
Yeah.
so it is like we are selecting edges which are cutting like both the cuts, right?
Yeah, which goes across, but only direction. We are conscious of the direction. Okay, so the direction should be from the set that contains S to the set that contains T. Okay, so for example, in this cut that I have described, so I am not considering the edge from this vertex to this with the capacity 10. So similarly, in this cut, which is from the book, so this edge, right, this is not contributing to the cut. So we are not interested in edges which are oriented from the set that contains T to the set that contains S. We are only looking at orientation from the set containing S to the set containing T. Okay. In the undirected sense, a cut would have been just this, all three edges. Okay. So here we are conscious of the direction. So that's why we call S to T cut.
Okay.
Yeah. So for example, in this example, I mean, it's the same graph there. So, okay. So if you had considered, so let's delete this. So if you had considered this cut, okay. So what, yeah, I can have this as a cut, right? So what are the edges that will contribute to the cut? Edge with weight 5, sorry. Edge with weight 5. This one. And what else? Edge with weight 20. This is edge with weight 10. So 20, 10, 30, 35 will be the value of the cut. Okay. So this edge will not contribute. Okay. Okay. So the corresponding computation problem is the min cut problem. Okay. So given the network with the capacity C, okay, and two distinct vertices S and T. So you want to output an ST cut of minimum, okay, so I won't use the term capacity, okay, let's use the term weight, okay, or minimum capacity cut or minimum weight cut, okay. So the duality comes because in the first object, that is flows, we are maximizing the value of the flow, whereas in the second object we are minimizing the value, okay. So there is this duality between max and min, okay. So it happens because this is a dual object, maximization becomes minimization here. Okay. So yeah, I just put the two pictures together. So this happens to be the minimum cut. You can verify, you can explore all possible cuts, that is by exploring all possible sets S and then taking its complement as T. Okay, so the set S should contain the vertex small s. Okay, then this happens to be the minimum cut, and that happens to be the value of the flow. Yeah. Okay. So again, I haven't proven to you that okay, this is the max flow. Okay. So we'll be doing it soon. Okay, so we'll be proving this min cut max flow theorem, which basically says maximum value of flow is the minimum weight of an S2T cut. Okay.
Hello, sir.
Yes.
Yeah, sir. Could you zoom in that diagram, below diagram?
Oh, it's not visible, is it? Sorry. Yeah. Is it better now?
What if I delete the flow which is having value 15 approaching to T?
What do you mean by delete the flow?
The 15 incoming flow for T.
15 incoming for T. Okay, so this one. Okay.
Yeah, if I delete that value, still the.
Yeah, still you'll be able to send 15.
Still the condition holds.
It does hold. Yeah. Also, no, if you remove 15, is the min cut is 15 only? It is, right? So if you remove this 15, you should be able to send a 15. Let's see. Oh, no, you'll be able to send only 10. Let's see, then the cut value should change, right? Let's see. Yeah, that's a good point. If you remove...
Sir, we will have a cut on C and T will be on one side and the other vertices
No,
will be
I
on
can
one
have a
side.
cut of size 10, right? Yeah, exactly. This one, right?
Yeah.
So that's a cut. So, yeah. Yeah, any other question? What is the time? Okay, 12:45. Okay.
It's 12:44.
Okay. So yeah, one request. So next Friday, can I have some 15-20 minutes of extra time just to put some concluding remarks and so on? So you don't have any activity soon after 1 o'clock, right? On Fridays? Not before 2. Okay, so I'll take 15 minutes extra next Friday, okay, so that I can put concluding remarks because I'll need a bit more time for at least two and a half lectures for NP completeness. So this, I mean, I'll just prove this lemma today, but max flow min cut, I think I'll need one more lecture. Okay. Okay, so let's start relating value of flow versus capacity. I mean weight of cut. Okay. So we'll start with a simple lemma. Okay. Basically says if you take any feasible S2T flow. Okay. Okay. So S2T flow. I'm bad at recognizing my own typos. And consider any S2T cut. Okay. Then we can show that the value of flow cannot be more than the weight of the cut or capacity of the cut. Okay. That is, flow at any point of time cannot be more than the size of the cut. Now, max flow min cut theorem. So this observation was made much before the max flow min cut theorem due to Ford and Fulkerson. Okay. So it went on showing that it's always possible to come up with a flow where this equality holds. Okay. So let's just see why this statement is true. This is basically simple manipulation of our definitions. Okay. So I'll just do it. So do it over a sequence of equations. Okay. Yeah. Is the statement clear to everyone? So give me any flow and give me any cut. Okay. So only condition is flow should be feasible. It should satisfy conservation property and it should meet the capacity constraints. That is, every edge, the flow assigned value should be less than or equal to the capacity. Then I can show that the flow value cannot be more than the value of the cut. Okay. So what does it mean? So see, I didn't say anything about the cut. I didn't say that this is minimum cut, nor did I say anything about the flow. Only condition that I put is flow should be feasible. Cut should be a cut. That's it. What does it immediately give us? So now we can maximize, right? We can choose F to be maximum value flow. Okay. Even then this statement holds for any cut. Then I can choose cut to be minimum weight cut or minimum capacity cut. So this effectively says max flow value less than or equal to minimum weight of a cut. Okay. This lemma essentially implies that max flow value is at most the minimum weight of cut. The next theorem, the punch theorem, basically says there is a flow F such that value is equal to minimum cut. So this lemma is simpler to prove. We'll start with proof of that. Later on, we'll see how to construct such a flow where this condition is met. That is, it matches the value of minimum cut. Is the statement clear to everyone? The statement is effectively saying maximum flow value is at most minimum weight of an S2T cut. Okay. Yeah, so the proof is basically simple manipulations of expressions, basically from definition. Okay. So by definition, value, so F be any flow. Okay. So F be any feasible flow. So by definition of feasibility, so we know that, I mean, not just feasibility, I mean conservation. So by definition, value of flow is nothing but dou of Fs. Okay. Now what I do is I take sum of dou's of all vertices in S. So I have a cut as well, right? I have a cut here. Okay. This is S. This is T. This is T here. This is S here. Okay. So there are some edges and so on. Sorry. Now what I do is I look at all vertices here, sum their net outflow value. Okay, that is dou of Fv. Remember that except for S, everyone will here contribute to 0. So hence this is equal to dou of Fs or value of F. So value of F is equal to this sum. Let's just expand it out. What is dou of Fv? It's basically sum of flows for all outgoing edges from U and then V, and then you subtract from it sum of flows of all incoming edges to V. Okay, so this is basically expansion. So this is from the definition of Fv. Okay, so we didn't do anything magical here. Now let's rearrange it a bit further. Okay, I mean, I didn't do anything so far. So what I did was slight manipulation here. So if UV is not an edge or VU is not an edge in the graph, I assume that the flow assignment is 0. Okay. So then I can write this way. So here the summation was when there was an edge. So instead I'll just run over all V in S and then all U in V. Here all W in V instead of saying W E V is in E. By the assumption that, so assuming F UV is 0 for all UV not an edge. Okay. That's all I did. Now let's go further. Let's rearrange it further. So what I'm going to do is, yeah, so I just rewrote. So I took away this bracket. So this is how it looks like. Okay. Now what I do is I split this into two. So V as vertices, those are in S and those are not in S. Okay. Split the summation again. So first part is V in S summation U in V minus S. Similarly, V in S, W in V minus S. Okay. And then take the remaining, that is V in S, U in S, and V in S, W in S. That's all I did. I just split this summation, whether U is in S or U is not in S. So here I wrote this first portion as those not in S, the second portion as those in S. Similarly, I split this summation. Okay, so this is how it will look like. So now what is this value? Can somebody tell me?
Zero.
Yeah, 0. Any takers for that statement?
Because it is just we are calculating f of s comma s plus and minus f of s comma s.
Yeah, so for any VU, right, there is also so f of u VU here, the same thing will appear with the negative sign here, right? Because you're running through all elements in S in both sum ends. So there will be, so if for the choice VU here, so we will okay, so there's a problem with this index. Okay, I mean it could be a bit confusing. I should have used a completely different variables here. Okay, I used the same V and V here. Okay, it's fine. So for any VU here, for the same V, I can choose W as equal to VU. So I get FUV. So there is a bijection, or in other words, they cancel out. So this is equal to 0. Okay, so that's what we are going to use now. I've just rewritten it here. Okay, so this is the portion. This is equal to this. This cancels out. So this is equal to only this portion. Okay, so this is equal to 0. Okay. So now V minus S is nothing but T, right? Remember that S union T is a partition of V. Okay, so I can just rewrite this as V in S, U in T, F of VU minus V in S, W in T, F of WV. Okay. But now remember that the flow values are non-negative, right? It can be 0, but it will be non-negative always by definition. So this value, if at all, this will be greater than or equal to 0. Okay. Or in other words, I can say that this summation is upper bounded by only this portion. So if I have something like, say, A is less than or equal to B minus C, but if I know that C is greater than or equal to 0, this implies A is less than or equal to B, right? So I can write this. Okay, so what did we get? So I'll just rewrite again. So this is value of F, which is del of F of S, is less than or equal to this summation. Okay, so what is the big deal with the summation? So let's look at it further. Okay, so what we do is we use the feasibility condition. Now I know that F of VU is at most C of VU. Okay, so I use that. So this is less than or equal to this summation as F of VU is less than or equal to C of VU. Yeah. Now this is exactly the value of the S to T cut, right? I'm taking, so again, I'm assuming that if UV is not an edge or VU is not an edge, then the capacity is 0. Okay. So under that assumption, this is nothing but the value of the cut. So, or in other words, value of F is less than or equal to this value. So it is less than or equal to the value of the cut. Okay. So all we did is we just used the conservation. We did some rearrangement. We did a careful split of this summation. Once we split it, I mean, we basically looked at edges across the cut and edges within the partition S. Okay, so that's all we did. But for the edges within the partition, these flow values, this summation basically cancels out. So in other words, what we get is value of F is upper bounded by sum of values of flow of edges across the cut. That is basically edges from S to T. Okay, but then value of flow is bounded by the capacity, so hence value of flow is upper bounded by the capacity or weight of the cut. That's exactly what we wanted, right? That's exactly the statement. Value of F is bounded by the capacity of ST. This in turn feels that it proves that max flow value is at most minimum weight of an S2T cut. Okay. Now we are going to prove next that they are equal in the sense that max flow value is equal to minimum weight of S2T cut. That is obtained by constructing a flow where the value of the flow is equal to the minimum weight of a cut. Okay. Okay, so I'll stop here now. So in the next class, I'm going to prove this statement. Okay, so if we have a network, flow network, then maximum value of an ST flow is equal to minimum capacity of an S2T cut.
We have proved that, right?
No, we have just proved that max flow value is less than or equal to minimum capacity. We haven't proved equality.
Sir, like mathematically, can't we argue this way? Like the right quantity's minimum value is the left quantity, and the left quantity's maximum value is the right quantity.
No, that we haven't done, right? Yeah, if you prove that, then it's yes. That is.
But mathematically, can't we say directly from this as a corollary?
No, it does not. Right. The existence is. So, Srinivasa, can you stop the recording?